Hi, welcome to, I believe this is the fifth video or fourth video for this class. So let's recap where we are. So far we have only covered the basic mathematical tools that we will be using. We still haven't touched anything system dynamics related. Why? So this is the first lecture we actually try to get into the concepts that are directly related to the topic of systems dynamics. And the first step in analyzing any dynamical systems is to model them. So here we start with defining the basic principles to create mathematical models for specifically mechanical systems. We might get into electrical systems a bit later in the end of the course if time permits. But for this course, predominantly we focus on mechanical systems. And if you remember, the goal here is to represent any dynamical system by a set of differential equations. So we take a mechanical system, many linkages and springs and dampers and all of those, try to represent them with a set of ODEs, x dots equal some function of x's and u's, these states and inputs, and then with that mathematical model we can go and try to analyze the behavior of system over time. So let's begin by talking about modeling of mechanical systems. But before we get to the modeling part, let's take a moment and discuss the idea of degrees of freedom. It gives us a very good idea, if we know what the degrees of freedom of a system is, how many equations, ODEs, is needed to describe it. So start with that. What is degree of freedom? A degree of freedom in its simple form is defined as the number of independent variables that uniquely define the state or configuration of a system. So if we have a complex system, for instance my body, if I pose in a certain situation how many variables or how much information you need to distinguish me from in this position than that position. So this is the idea of degrees of freedom. Let's maybe look at a few examples, really what we can take out of this definition, a few examples. So take, in the simplest case, a point on a line. So I have a line and a point. Let me try a different color. This point. So this very simple system, a line and a point on it, has 1 degree of freedom. Usually we know use abbreviation DOF, degree of freedom. This system has 1 degree of freedom because, for instance, if we are taking some reference, if you know the distance of your point from that reference, you can fully describe the system. It doesn't matter if the line is a straight line. For instance, if you have a curve, you can do the same thing. If you have a reference point and you have a point that is moving along that line, as long as you know the distance that the point has traveled to reach to its current location, if you know that, you can describe the system fully. So this system has 1 degree of freedom. Another example could be a point on a plane. So now imagine I have a 2-dimensional space, and I have this point that is moving along the plane anywhere it wants. Now this system has 2 degrees of freedom, 2 DOFs, because to know exactly where it is, you need 2 variables, both the X and Y variables to define where it is. And in all of these cases, doesn't matter positive or negative, as long as you can measure that distance and describe the position of the point, it should work. So X and Y, let me put back here, your degree of freedom is X. So here your degree of freedom could be X and Y, these 2 variables, but this is not unique. You could also, let me try a different color. Is that a different color? Not really. What else do I have? Green. Let's try this red again. Okay, doesn't work. So you could also define it as some angle and a distance. Again, notice that changing the way you try to describe the system really doesn't change the degrees of freedom. Still, you need 2 variables. If you do that, you need R and theta to fully define where this point is on the plane. And this is very important and very fundamental, that the set of variables that you need to describe a system, the number, doesn't matter what sets of variables you choose. At the end of the day, you will need 2 variables to fully define. You cannot do it with 1, and if you use 3, you can be sure that at least 2 of them are dependent. So going back to the definition, they have to be independent of each other for these variables. All right. So maybe as the last example, another example, final example. So imagine now I have a linkage. This is a famous linkage called a 4-bar mechanism. So these 2 points are fixed to the ground, and these are just pin joints that the links can rotate freely about those. This system has, I pause a few seconds, think how many degrees of freedom the system has. 3, 2, 1. So this system has 1 degree of freedom because, for instance, knowing this angle, if you move this, your entire mechanism uniquely move to a new position as you change theta. So only if you know theta, you can fully describe where the system is. So this system, the 4-bar mechanism, has 1 degree of freedom. And similar to the case here, it really doesn't matter which variable you use. It could be theta 1, or you could describe it with theta 2, or with theta 3, or with theta 4. Any of those would work. It is also possible to, I don't know, sometimes it is useful to extend your system, and this is called a coupler point, if I recall correctly. So as you move your mechanism around, this point follows a certain closed path. And you could also define your independent variable as the distance that this point has traversed from some reference point along the path. And this could also fully describe your system. If you know where the coupler point is on this curve, you can know exactly where the rest of the mechanism is. So that also brings me to an important concept very related to degree of freedom, and it's the matter of constraints. That there is a very tight relationship between degrees of freedom and constraints and the number of links in a system. So you have a bunch of links. Each of them potentially could move around in this space. That increases your degree of freedom. But because they are constrained to remain in certain positions relative to each other, that decreases back the degree of freedom. So I don't get into much of that, but there is a very cool relationship and equations that probably are better suited for the mechanisms course and design of machines. But I just wanted to point this out. Before I show you a few more examples, I just want to bridge this, the concept of degree of freedom, back to modeling and why it is important. In mechanical systems, it is almost universally true. In reality, it is absolutely true. And in approximations, usually true too, that every degree, let me put it this way, for every degree of freedom, you need one second order differential equation. So it is always true as long as you have inertia in the system. All your degrees of freedom has masses related to them. This leads to a second order differential equation, and maybe you can see already why. So one inertia, when it wants to move, we had the relation mx double dot equals some forces. So this is where the degree of freedom and the second order differential equation come into play. There are a few examples that we can discuss in this course that does not follow this rule, and those are more or less non-physical cases that we ignore the mass in the system. But as a general rule, whenever you have a degree of freedom that has a mass or inertia, you need one second order differential equation related to that degree of freedom. So this is a very good guiding principle and a check. If you have a complex mechanism that you know is, I don't know, 8 degrees of freedom, and you solve it, you came up with 2 equations, you probably know something went wrong. You need more equations. two in a specifically 1 second order differential equation per degree of freedom. All right, so I'm going to show a few examples, and I'm just going to write the solutions without going into details of why these systems have certain degrees of freedom. Think about it and try to convince yourself why it is true. So some examples. So imagine I have one mass that is rigidly, this is rigid, attached to another mass, and it moves in a plane. So how many degrees of freedom this system has? I could also do the same thing. Two masses, 2 point masses. These are point mass that connected to each other by a spring. I have one link. I put it here. One mass here, one mass here. This is a seesaw. What was it? Seesaw? Seesaw. The rigid link rotates about this point, and two masses are attached to the two ends. How does my example look? These are springs, two masses connected to two rigid walls, and for this case only imagine or consider movements in the in one direction, horizontal direction. Forget about, well, actually no, maybe both. Why not? Why not? Moving, both of them move on a plane. One more example. I have a cart, a pendulum, and a mass on top. So this is a pin joint that it can rotate about, and the cart can go back and forth. It is attached by a spring and a damper between two walls. And two more examples. How many links do I have? 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. And these are pinned to the ground. And the last one is a rope. So, how many degrees of freedom this is? I'm going to write down the answers, but think about why. So this one has 3. This one has 4. This one has 1. If I consider movement on a plane, this one has 4. If I consider, let me put it this way. This is if the masses move in 2-dimensional space, and it has 2 only if masses move in one direction. This one has 2. This one has 3. I'm not going to write that down. Think about it. We can discuss it in class. All right, so let me clean up the board and we can continue. All right. So now that we have checked the degree of freedom of the systems, now let's go into working with different components and try to build models of mechanical systems. So I think it's good to start by looking at different mechanical components that often show up in simple mechanical system. And it is a very good idea to try to think of different components in terms of their energy properties. And if you look at a system as a flow and change of energy within components of a system, first of all, it makes intuition and analysis a lot easier, and also it is very convenient way to relate different systems from different domains, for instance mechanical to electrical, or systems that involve hydraulic and other forms of energy, either represent one system as another or combine them together as a multi-domain system and analyze those. So considering the energy is a very convenient way to classify systems and components. I think a very good starting point is to classify mechanical components into 4 categories. One category are inertial elements or components. And these kind of components can store kinetic energy. The second class is stiffness elements, and these ones store potential energy. A third one doesn't store energy but dissipates energy. So we have damping elements. These dissipate energy. So these two first elements do not get the energy out of the system or pump energy into the system. It is possible that potential and kinetic energy goes back and forth between these forms and is stored in these 2 different elements. Damping doesn't keep the total energy of the system the same. It reduces the total energy and usually turns it into heat, but not necessarily. And the last one, before talking about them, these are all in some sense passive elements, in the sense that the energy does not come from an external source or a different source of energy into the system. The last one is active elements. My marker is dying, I think. And these add or let me think of it this way. Add or extract energy. Add energy to the system or extract it. And usually, I can't think of an example that isn't the case. There is a form of energy conversion into another field. For instance, I'll talk about it, but an electric motor takes electrical energy and converts it to mechanical, or the reverse of that, a generator can extract energy from a mechanical system and convert it to electrical. So these are the 4 common elements. This one is really dying. Maybe I should do this. Does it help? Yes, it helps. I hope. So these are the 4 common elements that we find in simple mechanical systems that we deal mostly in this course. So now let's go a little deeper into each of those, and I start with inertia. Inertia needs an eye. So if you recall from dynamics or from physics, inertia is a property of matter that resists change in speed or resists change in momentum of the system. Although inertia is basically a linear or rectilinear, to be more correct in terms of terminology, a rectilinear system, but it can manifest in 2 ways, either rectilinear inertia or rotational inertia. But remember, very deep down, both of them are the same thing, acting in different domains. So linear or rectilinear inertia is the one that we are more familiar with, and we have this relation that m, mass or inertia, times acceleration, some form of position, second derivative of position, equal the net forces acting on that mass. So in this case, when we are talking about rectilinear aspects of movement, the kinetic energy, oh no, we describe it by T. I have T later. I should have T. Well, T, torque. No, let me keep it as E, energy. E equals a half m x dot squared. So this is the kind of mass that we have. It's moving not necessarily along a straight line. It can move in 2D. Then in that case, this x would be a 2-dimensional vector. But we're talking about translation of mass here. Another way inertia manifests is rotational. Rotational inertia. And you have seen this form in dynamics, that we had J theta double dot equals the net torque acting on the system. And for this course, we are usually talking about bodies or masses or inertias that are rotating about a fixed axis. So in this case, both J and Tj being the moment of inertia about that axis, and torque, both of them are about the axis of rotation.
And you should probably remember that J is moment of inertia, integral over the entire mass of r squared dm. This is over the entire mass of the system. This is moment of inertia, and r is the distance from the axis of rotation to any point along in the body. And in this case, the kinetic energy that is associated with this rotation system, very similar to the form for a translational mass, is a half j theta dot squared. Let me see. So maybe I can reiterate what this, for the sake of completeness. Imagine there is one system, maybe a disk or any other object that is rotating. The rotational equation is 1 point, if we take on the body, how much it is rotating relative to a fixed reference. This is what we call a rotational motion. And for the translation, I have, let's take it as a one-dimensional from some reference. This is x. This we call it m. We call that j, moment of inertia. And let me be utterly complete. Maybe I have some f and some torque. So this is a rotational element. The next element we can discuss is a stiffness element. I did a box for the other one. Stiffness. Stiffness is a little maybe trickier, maybe easy. I don't know about your intuition, but the stiffness is any device, any device, component, system, any device. I put it in quote. Any device that stores potential energy. I rewrote it again, it was here too, but I wanted to emphasize something here. That potential energy, if you recall, also come from the interaction of two masses, two inertias, that are acting at a distance, essentially the effect of gravity. That two-body system or device also stores potential energy, and it is an element. Usually what we are dealing with, one of the bodies is the ground, so we don't see it as two bodies, but we look at a single mass and its relation to Earth, the height of it basically, and that gives us another component that stores kinetic energy, and it classifies as a stiffness element. Maybe a little technical, you don't need to worry too much about it, but I like to think of it this way, that stiffness is defined for any component whose force can be defined as a gradient of a potential function, and potential function is a function that is only a a function of position. So this is maybe a side note, but if you, for instance, look at a spring that is attached to another point, it is on an xy plane, the potential function can look like something like this. It's a ball that is v. This is x and y. This is v. And f being the gradient. Gradient means the slope along the largest descent. So the direction of the force is always acting toward the center, and that is up here too, and that is the mathematical way why a spring is a stiffness element that stores potential energy. Anyways, you can safely ignore that, but it's fine. The common examples of these stiffness elements that we have seen. So again, going back to these two separate domains, translational and rotational domain. Translational, yeah, that's a better word. I'm going to translational, rectilinear, translation. Let's call it translation. Translational inertia, that's better. Okay. Now going back to the same two domains and looking at our old school spring, a translational spring if you recall, we had this spring that looks like that. It was fixed maybe to one end. Doesn't matter if it's fixed or not. It has a resting length of x naught, and it is being stretched to amount x. Then in this case, the force of a spring, F of S, equals minus k x minus x naught. And it is easy to visualize this minus. If I pull this in and move x forward, so my x is positive, it's bigger than x naught, the force is going to be in the opposite direction of x. Hence, this negative. And this is obviously can be the vector form by putting the vector, well, not exactly like that. Never mind, it's going to be a little more complicated. The shape of the equation, so it's going to be vector of this, and then a norm of it, and then a direction of it. It's fine. Let's keep it as is for now. Let me, similar to here, and the energy that is stored in terms of potential energy in this element, if you recall, is a half k x squared minus x naught squared. And that is the potential energy stored in this system, in this component. Similar to here, I can define a rotational spring that acts on rotational movements. It's harder to show it on a, usually it looks like that, from a reference how much it is rotated, theta, from some theta naught. And the torque in this case, because we are talking about rotations, torque of this spring is in a very similar form, k theta minus theta naught. And theta naught is the resting state of the spring. And the energy is a half k theta minus theta naught squared. So let me put it here as minus k delta x. This is minus k delta theta. And basically any element whose force is some k times change in position, that is a stiffness element and it stores potential energy, including gravity. And if you recall, force of gravity is minus g, well, mg. Wait a second. Let me think. mg, it doesn't come out as that form, mg, so let me think. I'm trying to think. How can I generalize it to gravity? Okay, I think, no, not, it has to come from this definition, not that form. That when we have force of gravity, this potential field for gravity close to Earth is uniform instead of having this bowl shape. So it's a uniform, it's a plane, and the gradient of that becomes this constant. But it follows from the original principle. So these are the kind of stiffnesses that we usually think as a stiffness. But also gravity is another form of stiffness. Instead of the force being related to change in position, force is constant, but still it always wants to return your object back to a certain position, to the center of the Earth, basically. So maybe let me finish this, that the energy, the potential energy that comes from the effect of gravity, if you recall, was minus mg delta y. And delta y was the change of height from some reference that was usually arbitrarily chosen. Okay. And one last thing about stiffness elements, is the concept of linear and nonlinear springs. So both of these relations that we discussed, there are examples of linear springs. If you plot x or theta and the force of this spring for this system, assuming that x naught is 0, otherwise you will have a you would shift the line up and down. This is the kind of force this system have with a slope of k being constant, but that does not necessarily need to be the case for an element to be stiffness. The stiffness element can also be nonlinear, and the force may change nonlinearly with the angle. They can also store potential energy, but they are a little more difficult to work with. They lead to a nonlinear differential equation and a nonlinear system that we usually do not consider in this course. An example of such nonlinear systems, you can construct those very simply. If you have a spring that becomes the distance between coils becomes smaller, so as you press it, the coils start to come in contact with each other, and essentially they become ineffective in the rest of the response. So as you push it, the spring force becomes larger and larger because now you're acting at a smaller distance. So this is an example of a nonlinear spring that I think it is used often. Maybe in automotive. No, those are mostly linear springs. But anyway, this is a very simple way to construct a nonlinear spring. And maybe one last thing about the spring before I stop and clear the board. In reality, again going back to the discussion we always had, in reality everything is nonlinear, and usually the springs we work with are linear enough with a very good approximation. But even if you try really hard, there is still some non-uniformity within the material, and the changes of the Young's modulus, for instance, as you maybe push your material a little more, all of those might lead to a slight nonlinearity, but we often ignore those with our regular springs. Okay, so let me clean up the board and we come back with the other two elements, and that should be close to the end of this lecture. All right, so the next item that we have, the next component, is a damper. A damper is any passive element or device that takes the energy from system and usually converts it into heat. The difference between a damper and an active system that takes energy is the way the damper, the stereotypical or characteristic way the damper takes energy from a system. If an element, let me put it, if the direction, if the direction of an element force is opposite of its velocity, we have a damper. So the reason you can think of it is simple. So if the force is always in the opposite of velocity, so I'm going this way, and I'm always pulling it back wherever it's going, I always pull back. I'll get into this a bit later, but the displacement times force, F dot dr is always going to be negative. So that element always does negative work. And it turns that work into heat often. So this kind of element always takes out energy from the system. Again, if I look at a linear or translational damper, or rectilinear, translational, in a translational domain, I have usually we show damper with such such symbol. So if one side is having this kind of velocity, that side has that kind of velocity. The F, the force of damper, is C, essentially the rate of change of lengthening. It's minus C, I'm going to call it L dot. And this L dot is rate of change of length. So it always is, if it is lengthening in that direction, the force, it's going to create a resistance force, Fd. Similarly, in a rotational damper, I really don't know how to show it as a symbol. I'm going to do this, but maybe that's not the universal symbol. Again, the torque is minus C theta dot. Theta dot being the rate of change in its angular length. And both of these types take energy out of the system and convert it to heat. Again, these two are linear kinds of dampers, because if you plot theta dot or L dot and force or torque, it's going to look like a line. But that doesn't need to be a case. There are different potential ways an element can take energy out of system, although not in a nonlinear way. Coulomb friction or the kinetic friction, that kind of force also takes out energy from the system, converts it to heat. Aerodynamic drag also works in the same way. The force is always in the direction of the movement, but in that case, well, let me write it. Here, force is constant, or it depends on the compression of the two surfaces together. And in this case, force is some constant V squared. So here we had only x, where is it? V or theta dot. Here the force changes with a squared of velocity. These two, both of them are nonlinear forms of damper elements that can work in the same way as a damper, but we usually do not work with those in this course because they make the system nonlinear. We stick with this type. And similar to a spring, all dampers are essentially nonlinear, but we often, if we are within the operating range of a damper, the nonlinearities are small, and we can, with good approximation, assume they are linear. That's that. And the last element, the active elements, are those, there are no specific characteristic equation that you can attribute to an active element. They can do anything to your system. But the common aspects of what makes a component active is usually they transform one form of energy to another. For instance, an electric motor that works in a rotational domain transforms electricity to mechanical torque, or working as a generator takes out or does negative work and puts it back into electrical form. Usually there is this energy conversion, and you can control the operation of your active element to do whatever you want, regardless of these structured forces. And that is what makes really good use, makes them useful in our applications. So maybe if, as an example for active elements that are in translational domain, you can think of a linear motor. It's an electromagnetic, electromechanical system that essentially moves along a rail. A hydraulic pump, or no, hydraulic jack, a pneumatic jack, all of those are active elements in translational domain that you can control the amount of force however you want. In rotational, we can have electric motor, an internal combustion engine, a turbine, a rotational hydraulic motor, to name a few. So these active elements, let me just write something here, often convert one form of energy to another. And another piece of information here, arbitrary F or T you can get out of them. Okay, so that is that. Maybe I have enough space here to do a quick example. This one is dying. Wait, what is happening? Oh, I can't do this. Okay, I get it. Example. I have to press it. So let's look at an extremely simple yet fundamental form of system that we deal in this course. Let's assume we have a mass that is moving along this horizontal track. We have a damper with coefficient B, a stiffness with spring constant K, and the system is just moving around under the influence of those forces. We want to find the equations of motion for this system. So one thing that is extremely important, always what we do is start from free body diagram. So I have, this is my mass, M. It is important to define some positive direction for yourself. And this is the distance, x, of the mass from some reference from the wall. And let's pretend this spring has its resting length at 0, x equals 0. So if I draw the free body diagram of this mass, so let's see how we can do this. Originally my mass was here, and I have stretched it to some positive value x. That causes a force in the opposite direction to the amount of kx. So if x is positive, my force is going to be in that direction. If you want to make it in vector form, is minus kx. Same thing for damper. If I have a velocity, I'm pulling the mass in the positive x direction, the damper is resisting the motion. So the force is also going to be backward. Fd equals bx dot. I'm going to keep this minus. And these are the two forces. I'm going to ignore the gravity and normal force because I don't worry too much about the movement in the other direction. And one thing before going into writing the equation of motion, this system, assuming that the mass only moves along this line, horizontal line, has 1 degree of freedom. 1 degree of freedom, 1 DOF. So from the get-go, I know I should expect to have one second order differential equation because I have a mass. I have a mass, and that mass has 1 degree of freedom. I should have a single second order differential equation. Let's see if we can get to that. And if I write equations of motion for this, I have sum of forces along x direction equals ma, right? And for that I have mx double dot equals minus kx minus bx dot. And if I rearrange those, mx double dot plus bx dot plus kx equals 0. And this is what we call equation of motion or equation of motion. Sometimes, usually it's not abbreviated as EOM, but for the sake of brevity, I do it now here. Sometimes it is written as EOM. So that is the equation of motion of this very simple mechanical system. And now let's very quickly analyze maybe some movements. For a start, let's assume there is no damping, so B equals 0. No damping, which means we know if there is no damping, we only have the stiffness element and the inertia element. The two forms of energy that can exist in this system is potential and kinetic energy, and because there is no damping to take energy out of system, the energy should remain constant. So total energy conserved. This is what we know. So whatever happens to the system, we know the total energy should remain the same, and if we have potential energy, it may be converted to kinetic energy and vice versa. So let's solve that. For simplicity, well, actually we have solved this before. Go back to the last lecture and we exactly solved this. And x of t with the initial condition of pulling x 1 meter and then letting it go is going to be, if we pull it 1 meter, cosine of omega n t. And if you recall, omega n was the square root of k over m, what we call the natural frequency of the system. And the system's response looks like this. It starts from 1, and it's a cosine function that goes back and forth. This is t, x of t. And in the extremums of this curve, these are where you can see the slope of this curve is 0. The slope of x, or derivative of x, is velocity. So I don't have velocity here, and meaning that there is no kinetic energy in those points, and the entire energy is potential energy only. Conversely, assuming that we assumed the resting length of x is 0, so at these points, and this point too, we do not have any potential energy. And again, if you look at the slope, the velocity, or the speed, is maximum at these points. So these are, we only have kinetic energy, and that is the only form of energy that we have in this system at those times. And maybe if I quickly look at another case, let me do it here because I may need a little more space. If there is some damping, in this case the total energy of system is going to decrease because damping is reducing the total energy of system as the time progresses. I'll get into more details of the system response in a few lectures, but very quickly looking at it, the system's response is going to look like something like this. So it is going to be x of t is going to be some e to the power minus some constant value t cosine of omega, no, not omega n, omega dt. It's going to be a slightly different frequency. But as you can see, at these extremums, for instance, that we only have potential energy, it is constantly decreasing and converging to 0. So this damping element is eating into your total energy and eventually bring the entire system to a stop. So I have one more example, quick example before we finish. Let me quickly clean the board and we can do the final example and wrap this lecture up. Okay, so let's do another quick example and we wrap this lecture off. Wrap it up. So I have here another system, I have a spring and a damper that are being pulled by some force F. Importantly, this example, we assume no mass. So this is one of the cases that I mentioned earlier, that we might approximate a system by ignoring the masses or all the inertias. It's not a real physical system because all physical systems have inertia, but if the inertias are relatively small compared to the size of the forces, it is possible to sometimes ignore them. And this example is one of those. So before going into the solution, pause this video for a second, think of how many degrees of freedom this system is, and what do you think you need as, how many equations and what form do you think you will need? So this system is a 1 degree of freedom system, 1 DOF, because if you only know the distance of this tip point, x, you can fully describe where it is and how it looks like. So it's a 1 degree of freedom system, but there is no mass. So it is likely that we do not need a second order differential equation, but let's see how it goes. So I'm going to start by drawing the free body diagram of this point. Although it's massless, still I can do that. This is, I believe, something we used to do in static course. I have some force F and some force F of a spring and some force F of damper. And the situation is the same. Pretend if you have, again, pretend the resting length of this spring is 0. So you start from here and you have pulled your system to this point. So this spring is going to resist in the opposite direction of x. Same for B. If you're moving in this direction, your damper is resisting that velocity. So if x is positive in that direction, the force of damper is in the opposite direction. And the equation of motion for this is going to be sum of F equals ma. That is what we had. Doesn't matter what direction we are looking at. Because mass is 0, we should have an equilibrium of forces. So sum of F equals 0. Now I have F in the positive, this is my positive direction. F minus Fs minus Fd equals 0. So F minus Ks minus B x dot equals 0. I'm just going to rewrite it here slightly nicer. B x dot, do I write it like that? No. X dot plus K over B x minus F over B, or 1B times F equals 0. That is my differential equation, or equation of motion. I arrived at a single first order differential equation. So if I had a mass here, I would end up with some mx double dot that would turn it into a second order. Because I don't have a mass, that second order does not show up, and we end up with just one first order differential equation. And let's maybe, as an exercise, try to use this with Laplace transform with the initial condition of x of 0 and x dot of 0 equals 0. So the system starts at rest, and my f of t is going to be just a step function. So it's going to be 0, maybe with a different color. It's going to be 0 and jumps at some value f naught. So let's do this. F of t equals some f naught u of t. This is t. This is f of t. So taking the Laplace transform of this entire equation, I have Sx minus x of 0. That is the first thing. Plus k over b x of s. Let me put x of s. Is x of s minus 1 over b Laplace transform of f of s, which, because f is a step function, is going to be f naught over s. Take a moment to think about this relation, how it makes sense. Equals 0. We said this one is 0, so we do not need to worry about that. So I have x of s times s plus k over b equals f naught over b 1 over s, or my x of s equals f naught over b 1 over s plus k over b. Okay. And if, well, this part is constant, we don't worry about that. 1 over s times s plus a. If you recall, that from the table is 1 minus e to the minus at, assuming this whole thing is called a. So from here, x of t is going to be f naught over b. I think I missed, yes, 1a in my narration. So it's, let's call this a. Do I want to call that a? Let's call it a. It's going to be 1 over a times 1 minus e to the minus at. And a is k over b. So this will be b over k. And this one is going to be k over b. I'm going to write it this way. Minus t over b over k. That's better. And this b cancels with that. And what I'm left with is f naught over k 1 minus e to the minus t over tau. And here my tau is b over k. It is called time constant. Time constant of this first order system. And let's look at it, how it looks like. Oops. So if I draw this This is time, this is x of t. So before I plot it, even if you don't see this, you can intuit what is happening. So I have this system. I immediately start applying some force, some constant force. This spring has no problem being instantaneous. It can do whatever it wants, and it can jump. But damper needs time to develop and move because its velocity is dependent on the force. Immediately there is going to be a large velocity because there is a force, but as you start pulling it, now K, the spring, starts to apply some resisting force, meaning B doesn't need to work as hard to combat that F. So the system starts to slow down until you eventually reach almost a stop, and the entire force, this force is going to be resisted by this spring force. And in that case, the force of the spring, Kx, is going to be equal F or F naught. And this is what we have here. So eventually, the length of the spring is going to reach that. And this is exactly what this equation is telling us. So eventually, we are going to reach at F naught over K. And originally, we have very large velocity. And we are going to slow down until we asymptotically reach that value. And this time constant, the ratio between damping and spring stiffness, defines how fast or slow we arrive. If my damping is too strong, so my damper is going to respond very slowly and relax very slowly. So it's going to be a very slow rise. This is an exponential function, but anyways. Instead, if my spring is very strong, one effect is moving this down. The other one, if B is very small, essentially if it is non-existent, the system is going to respond almost instantaneously and do that. So this time constant defines how fast or slow my system is progressing. And this is a very common parameter in first order differential equation systems or first order systems, that all of them have this generic form of exponential growth or exponential, not growth, exponential asymptotic to a certain value, or exponential decay with a time constant of this form. Okay, so that is all I have for today. Let me check. Yes, that's all we have. This was a longer lecture. Because there was a lot to cover, I didn't want to cut it off somewhere in the middle. But the next one is going to be shorter. So stay tuned for that. See you then.